Hello everyone, this is Mark Peterson from CamLogic, and welcome to today's webinar brought to you by CamLogic and featuring Moldex3D, a leader in today's CAE solution space. Moldex3D provides simulation solutions for some of the largest and most successful injection molding manufacturers in the world today, and they are a company that CamLogic is proud to represent out in the precision manufacturing marketplace. Presenting today will be Rob Stepek from Moldex3D, who will show you that what they are offering is the absolute best-in-class simulation analysis in today's plastic injection mold environment. He'll show how Moldex is helping customers to troubleshoot from product design to development, to optimize design pattern, shorten time to market, and maximize product ROI. In addition, their compatibility with mainstream CAD systems allows for easy integration into your process. Let's start by familiarizing everyone with CamLogic. CamLogic has been in this CAD/CAM CAE space for over 35 years. We were established 16 years ago, focused initially on CAM, servicing mainly the tool and die shops in the area. As the market evolved, CamLogic has also evolved. Interestingly, working our way backward from manufacturing back to the conception of the idea or design. And because we started toward the end of the process and worked our way to the beginning, CamLogic has the fundamental knowledge of what has to be done to assure that each step of the process will result in a product that will actually work or fit into the next phase of development. CamLogic has chosen to represent software and tools that enable our customers to fulfill the full cycle of product development. And we consider ourselves integrators and partners for our customers, not just resellers. CamLogic employs the three-legged stool strategy. We partner with Siemens and Esprit, offering the complete integrated portfolio for design, manufacturing, analysis, data storage, and retrieval. And we partner with 3D Systems for 3D printing and rapid prototyping, and Romer and Creaform for 3D scanning and inspection and quality. And Moldex3D obviously is in the PLM space for the very best in simulation for your molds. And now that you've heard a little bit about CamLogic, I'll hand you off to Rob Stepek from Moldex, who can take a deeper dive into their solutions.
Okay, I'll bring this up. Well, first off, good afternoon, everyone. Hope everybody's having a great Thursday. My name is Rob Stepek, and I work as the Business Development Specialist here at Moldex3D. I will be taking us through today's webinar. So first, let me start by giving you a little bit of background on Moldex3D and CoreTech systems. Headquartered in Hsinchu, Taiwan, CoreTech Systems has grown to be the largest independent CAE software provider in plastic injection molding. CoreTech System provides world-class solutions through many experienced engineering professionals and convenient sales locations. Today, CoreTech offers sales and support to more than 160 international resellers and 9 direct offices worldwide. In order to meet the various demands of our global customers, CoreTech Systems has partnered up with strategic alliances such as PTC, Dassault, Siemens, Cimatron, Altair, and many, many others so that we can create more value for our customers. In addition to the benefits that Moldex3D provides, our experienced engineering professionals strive to provide technical support and guarantee customer satisfaction. Many prestigious companies have implemented Moldex3D as a solution, as you can see here. We are on a constant journey to improve Moldex3D for the fast-evolving plastic industry. While focusing on improving user experience and consistent computing results, we strive for best quality and expansion of our applications. Over the last 30 years or so, Moldex3D has been an industry leader and innovator, from being the first to do 3D meshing to our exclusive ability to run MuCell simulations. We are not just consistently improving our software results, but also in the speed in which our results are generated through our ability to do parallel computing. Moldex3D was originally started as an academic project about 20 years ago, and again has consistently improved with each generation of Moldex3D. And now I'll get into a little bit about what our software does. First, I'll start with flow analysis. Moldex3D predicts melt fronts, weld lines, air traps, short shots, and other problems that can occur during filling analysis. This also includes unbalanced filling and thermodegradation of plastics. With this feature, you can save time and money by catching potential problems before a part is manufactured. And here you can see our flow analysis running. You can also see in the picture below there with the little red dots where weld lines would be predicted in this particular flow. Here we'll talk a little bit about packing analysis. During the packing phase, Moldex3D can simulate the density variation and melt flow due to material compressibility. On the left side, we see the packing density of the plastic at the end of the packing phase. And on the right side, we see an animation of the slicing function, which cuts a plane through the model. This allows us to see what is occurring on that plane throughout the model. On the right, you can see volumetric shrinkage, which is a percentage that the plastic has shrunk during the packing phase. The animation shows an isosurface display, which shows the solid element that corresponds to a specific value. We usually use this to find high volumetric shrinkage. These areas tend to also correlate with areas that are prone to either voids and or sink marks. Here's a little bit about cooling analysis. This simulates mold temperature, cooling, efficiencies, hot spots, and cooling time. Below we see 3 pictures. Each of these pictures is of the same model. The first one shows the cooling temperature inside the cavity. This is the temperature of the cavity has reached at the end of cooling. This can be used to find hot spots within your plastic. That second picture there depicts cooling efficiency. This shows the amount of heat each individual cooling line will lose. And with this tool, you can detect inefficient cooling lines that can be removed, which in turn save you money with tooling costs later on. And lastly, on the right, you can see the slicing function of the cooling temperature of the mold base. This shows you just how warm or cold the temperature distribution is within the mold base at the end of cooling. Warp analysis. These animations will show you exactly how your part will warp. Part warpage, as many of you know, is due to volumetric shrinkage, and our software gives you the ability to further help control these defects before your mold is actually built. Fiber analysis. This is an add-on solution that simulates 3D fiber orientation and calculates the process-induced anisotropic properties. This animation shows the slicing function that cuts through the part. You can see in detail the various directions of the fibers inside the part. And in the right-hand corner, you can see a close-up of the fiber. This shows the concentration and the direction of the fibers in that particular area. MCM, or multi-component molding. With this tool, you'll be able to simulate part inserts, mold inserts, and two-shot molding, also called overmolding. Here we can see the flow simulation of plastic over a part insert, as well as the warpage that is resulting from this flow process. Visco elasticity. With this tool, we can predict flow-induced residual stress and prevent the potential design problems. In the pictures below, we can see the predicted residual stress calculated by our solver and the actual residual stress observed in the chemical test. And based on the two images, you can see that our solver has predicted where the results would be, and we're accurate with the chemical test. Optics. Moldex3D can precisely predict bend refringence caused by the complicated process-induced anisotropy in the cavity. In this picture below, we can see the predicted bend refringence as determined by our solver and the actual bend refringence. And again, our predictions and results were accurate with the actual test. FEA Interface. Our FEA interface is a series of interface modules that integrate Moldex3D and structural CAE software like Abacus. With this, you will be able to export fiber orientation data into these structural CAE softwares and test the model with various loads as well as the natural frequencies of whatever the structural analysis offers. Below we can see the comparison of a part that is fiber-filled and one that is not. And as you can see from the pictures below, the one with fiber has much less displacement than the one without. Our database. Inside our database, we have well over 6,000 different materials that a user can use. Users can also export the materials into the user bank to modify the material data so that it will fit better within their analysis. Analysis benchmark. This slide demonstrates the advantages of parallel processing. With parallel processing, the time needed to run an analysis can be substantially reduced. For example, if you have a desktop computer with a 4-core i7 CPU, the flow pack analysis of a model with 1 million elements can typically be finished in about an hour, and cool warp analysis usually gets finished in about half that time. And if you're asking how this is possible, well, it's because with parallel processing, the performer, you have the ability to attach more than one core to run an analysis and significantly reduce the amount of time needed to obtain the analysis results based on the number of cores that are added. Remote computing. The way the private cloud and the pay-per-view system will kind of be explained here. First, users would prepare a pre-processed data on the client-end computer. Next, they would submit analysis to a workstation. The workstation would then run a Moldex3D analysis. When that is finished, the users will be able to download the post-process results back onto the client computer and review these results to look at ways to optimize their design. Okay. Next, I'll show you guys just a quick demo of our software and how our software works. I have a Moldex3D's R11 on my computer. This is Moldex 3D Design. This is what we'll open first. Some of this here. Basically, the designer is where you actually build your solid mesh. You also create your runner system here, as well as check your mesh surface to make sure your part's okay. So again, I'll walk you through these 5 steps here. This is pretty simple and easy to understand and easy to learn. First step, you would want to import your part. So go to my part, and we're going to import a cell phone. So we'll start with the cell phone part. And we're going to select millimeters for this. And here we have our cell phone. And we imported this using a STL file. Also, we have an insert for this. And there we have our cell phone and these cell phone inserts. All right, next we'll move on to step 2, which is where you build your runner system. Let me get this set up. There we go. For this, we're going to use pin gates. But in the event that you didn't want to use a pin gate, you want to use, say, a tunnel gate that's located here. Basically, all your different types of gates are located here. Edge gates, tunnel gates, cashew gates, they're all right here. But for our sake, we're going to use a pin gate. And I want to put one right here. I just want to reduce the size of that. And then click OK. And I think I'm going to add another one and put one right here. Again, I'll just reduce that size. Okay, as you can see, we've added our pin gates. Next, I'm going to use the Runner Wizard function. And by clicking Runner Wizard, it automatically generates a runner system for you. Our software does. In the event that, say, you already had your runner system design, you could easily import your runner into the software. Or if you wanted to draw it, you would simply use the line function, and then you could designate your lines for whatever design for the runner system that you wanted. Here you also, if you wanted to pick a different parting direction, you could do that here. To 2-plate mold, 3-plate mold. It's all done here. If you double-click, you'll be able to identify shape and size for your runner, as well as whether you want it to be a hot runner or a cold runner. All that can be done here. So again, this is where you would change your shape and size in here. And click OK. Our melt entrance point has already been selected for us, so we're good and we don't have to worry about that. Step 3, we'll move on to constructing our mold base and cooling system. I'm going to use the mold wizard, but again, if you want to import this or sketch this, you absolutely could. But I'm just going to use our mold wizard to go ahead and generate a mold base for us. As you can see, we have our mold base, as well as this red line will be our parting line. But if you want to change your parting line, again, you could do that here. If you want to change the size of the mold base, you could do that here, like width. Again, if you want to change size, overall height, cavity, core, all right here. And click OK. And our mold base has been constructed. I think I'm going to go ahead and add a cooling channel to this as well. I just use Cooling Wizard. But again, this is totally customizable. You could sketch your cooling system however you wanted to. If you have your cooling lines in, you want to add more, just simply add more. If you want to put these along a different direction, like the Z, do that here. Okay. Change the diameter, you can do that here. Want to space them out a little bit. Again, totally customizable for however it is you would like to set this up. I'm going to go ahead and put in a connector operation. So we have connectors for our cooling lines now. Click OK. Then I'm going to use the inlet-outlet wizard, and this just kind of designates where your cooling solution will be going in and where it will be flowing out. And you can see by the arrows, this is where cooling goes in and cooling goes out. All right, now that we have this constructed, we can go ahead and set our solid mesh generator. Here is where you set the amount of elements that you want for your particular part. It's really up to you, however many elements or how fine you want your mesh to be. For demonstration purposes, I'm just going to set this at a level 2. Basically, if you're setting this at a level 1 or a level 2, you want really quick results. You don't really care for your results to be accurate. You just need like a ballpark idea of how your simulation is going to turn out. It just basically saves time. But if you want something that's very accurate, but and don't mind it being a little time-consuming, you would set your level to a level 5. Check options. Want to ensure that there's enough mesh layers, and you would click OK. So now this is set, and you would click Generate, and now you're generating your solid mesh. This generally, depending on the part and the amount of elements that you have and how intricate your part is, could take anywhere between, I'd say, 2 minutes to maybe 10 minutes to do. But I mean, for this part, it shouldn't take too long to create the solid mesh. And while this is creating, I'll show you guys. If you needed, some advice for how to build, just click that green arrow. I'll take you through some step-by-step advice. While this is generating, I'm going to bring up some of the results that I already have run for this. Here, I did a full analysis, which would be filling, packing, cooling, and warp. And here's where you get to see things like melt front time, our shear stress. We can indicate shear rate as well. You can identify where air traps and weld lines are. If you wanted to see exactly how melt flow would be, click play. And it shows you what the plastic's going to do when it enters into the cavity. Okay. About that. I'll see if we can bring up weld lines here. My computer's been running a little bit slow, but oh, there we go. Those red marks indicate where potential for your weld lines would be. If I click air traps, those blue dots indicate where potential air traps could be. So these are all things that, before you cut steel and build a mold, that you would definitely want to know before you built your part. If you want to check warpage of your part, see if we can bring this up. This gives you an idea of just how your part's going to warp. Is your X displacement, Y displacement, Z displacement. This part, we have some fiber in it, so you can kind of tell warpage fiber orientation here. You can tell volumetric shrink. It's just a good tool to let you know how things are going to happen before you actually produce the part. Let me go ahead and see if this is done. Okay. Yep, this is done creating the solid mesh. Now that our solid mesh has been created, you would go to step 5, which is where you would save and export your mesh. Click that. And I'm just going to save this to my desktop. Home part, save. And now it's just going to go through the process where it checks my solid mesh and actually saves it to that folder that I designated for this solid mesh. And again, this doesn't take too long. This is a pretty quick process. Let's give this a second here. Go ahead and I'll close this out. Don't need this anymore. There we go. We've been successfully saved and exported, and we should be able to move on to our next step, where we will go ahead and run an analysis. So that would be here, designer, or excuse me, project. I'm sorry. What is this? Not working. That's not good. Okay. You double-click the project manager, and you get this screen. And this, again, is your next step. And what we would do is we would create a new project. What are you doing here? Let me try this again. Okay, let's try this one more time. Okay, we're going to go through the steps of creating a new project here. We want to make sure that we're running this on classic mode. And this designates where our project name, where our project will be saved. We are running this in 3D. This is traditional injection molding. And if you want to go ahead and put together a project summary or who this is for, you could do this here. And once we have that all set up, click Finished. Now we will go through the steps of bringing in our mesh. So we will be creating a new run. I want to create new mesh. We'll get this from our desktop demo part, our cell phone. Give this a second. Again, my apologies for my computer running a little bit slow today. But our mesh has been brought in. We move on to the next step where we would choose our materials. I'll show you guys in the event that we had to bring in a new material, we would click New. Professional will stop working. Not good. Okay. Let me just try to import one instead. Materials. Here I'm importing a material because I already had it on my desktop. I'm going to try to show you guys how to bring in a new one from our data bank. Here we go. This is the Moldex 3D data bank that I was talking about earlier that had over 6,000 different materials in it. As you can see, it's organized by the different types of plastics, as well as the different producers here, and just what exactly we have for that producer. So if you didn't, per chance, happen to see what it was you were looking for, we can definitely find you a comparable material or get your material added to our data bank for us. That's no problem, or for you. That's no problem. I'll close out of this. And again, I have another material I want to import here for that part insert. This is a metal part that I have. Okay. And both of those materials have now been imported. Next step, we would choose our process. I'm going to click New Process. And our process conditions are all set here. Click Save. Move on to computation. And I want to show you guys really quick, when we were talking about parallel processing, this is where you would set that. You would go to Task Manager. And here's where you would set up if you had more computers that you wanted to run this on to get faster results. You could set that all here, as well as the amount of cores that you have running. It's all set here. I'll go ahead and click Next. This just check run data. We're all set. We'll finish that up. And here we have our part ready for analysis. And in order to run this particular part, you just double-click on Analysis and then pick. If you want to do filling, if you want to do filling packing, whatever it was you were looking for, you just designate that here and click Run Now, and you would be on your way to running an analysis. That's basically, in a nutshell, how our software works. Exit out of this, and I'll bring up PowerPoint. And I'm just going to go through a handful of case studies. Just kind of demonstrating how our software benefits the users. Let's see. Moldex 3D has the ability to help users reduce cooling time, reduce costs, improve part design, and these are just examples of that. Here we have a bracket gate location analysis. If you look at the picture on the left, you can see one model of a hinge. And the hinge only has one gate. The nominal thickness is 0.08, and the thickness of the hinge is 0.025. And in this case, because the hinge was rather thin and hard to fill, we were having short shot issues. And the picture on the right is the same model, except we added 2 gates to it. And because we added that second gate, we were able to fix the short shot problem. Here we have an axle mount. And what we were having issues with here was that because of the gate location, we were having an issue with the weld line. And our software was able to simulate where that weld line was, and we were able to move that gate location in order to strengthen the part and build a better quality part. With regards to the seat bracket, Moldex 3D has the ability to simulate multiple cavities. And based on the simulation of the software, is able to provide the weight of each cavity. In this chart, you can see in cavities 1 through 4, you have the ability to compare the simulation part weight and the actual weight, and the results were very, very accurate. Here we can see a harness slip. This is an example of a company using Moldex 3D to predict warpage. After simulating the warpage tendency and volume, we added windage to compensate in the CAD model. In this case, we were able to improve part quality by predicting the warpage and compensating for it. In this case, we will be looking at a syringe model. This case demonstrates how Moldex 3D can help you on your mold design to optimize the cooling system that you best need to reduce your cycle time. In this case, you can see some base information about the model. The client in this case was primarily concerned with cooling. We demonstrated how conformal cooling analysis would best suit their needs. We ran 3 tests, which you can see below. The first one was a baseline with no cooling channel or analysis. The second, we used a baffle system. And finally, we used a conformal cooling system here on the last one. Here you can see the results comparison. On this slide, we see the part temperature distribution at the end of cooling. We can see the temperature of the part has reduced by 10 degrees Celsius using the conformal cooling channels. Transient temperature results. Here we can see a slice of the mold base and the mold base temperature at the end of cooling. From these pictures, you can see that conformal cooling channels are not only cooler, but also high temperatures have moved back into the runner system. The baffle system, although it's better than nothing, wasn't exactly the best option. And the conformal cooling system, I mean, obviously by the changes, was definitely the clearly superior option. The results comparison. Finally, we'll quickly discuss cooling time. And as you can see here with the conformal cooling system, we were able to reduce the cooling time by about 1 second. So it was definitely a good improvement. Here we'll look at another case study involving a speed meter. We can see the cooling channel layout and the mesh used for the speed meter model. On this slide, we see the original design with the melt front at 80% and the original design with the Z displacement warpage. And below is a table with the warpage for the original design with design 2 insert. For the model, the user wanted to reduce warpage. The issue here was that the part insert was causing some problems. Because the insert was below the cavity, the warpage we were finding was non-uniform. For the first revised design, we decided that we should enlarge the gate dimensions to extend for the time of gate solidification and try to improve packing. In the second redesign model, we modified the runner layout to improve for a more balanced flow and packing effect from gates 2 to 6. In the layout number 2, we are trying to provide uniform packing pressure, so we can also try to reduce the volumetric shrinkage of the part. Here we see that in regards to the enlarged gate dimension, there really is no obvious difference between the original and the revised design. Here, although we see an improvement in packing efficiency from the enlarged gates, there is still non-uniform packing distribution within the cavity. Through this quick comparison between the revised design and the original, you can see the improvement in the X and Y direction, but the Z direction still has not improved much. And we'd probably like to get that to improve a little bit more. And here is the redesign number 2. For this design, we adopted a 3-point model system, which completely changed the runner layout. After modifying the runner layout, we found that the flow was more balanced, thus the non-uniform packing effect caused by an imbalanced flow was greatly reduced. With regards to pack analysis and pressure, here we see the pressure distribution inside the cavity. The packing pressure distribution here was a lot more uniform. This finally improved on the part warpage. And here below we can see the warpage of the original design versus the revised design, and the improvements were above 50%, which is great. And here is the final comparison of all the designs, and it shows the second redesign greatly improved warpage by providing that more balanced filling that we were looking for inside the cavity, which in turn provided more uniform packing and more uniform volumetric shrinkage. A handful of other success stories, just really quick. Here I'm going to talk a little bit about Moldex3D and our FEA interface. On these next slides, I just want to show everyone how Moldex3D's FEA interface can improve part quality. And what you see here is a TV neck which mounts on the back of a monitor which connects to the back of a TV. And during assembly, the breakage chances for the mounting holes, which are these guys here, which are also called bosses, increases. And therefore, this project aimed to leverage Moldex3D's FEA interface to get the material parameters, and then we used Abacus to simulate the locking torque process. And through the simulation, we can obtain the best results to increase the part's strength and improve the part quality. Oh, hold on a second. There you go. Sorry about that. Here we're just going to show you the thickness distribution of the bosses. A and B are here. Here's the thickness distribution for them. Here are the thickness distribution for the bosses C and D. And here's just some general parameters for what it was the part was used to make, the filling time, the melt temperature, mold temperature. Again, we can see the processing conditions here. And with this slide, we just want to show you the filling process. During the filling process, we're looking for air traps, weld lines, and short shot issues that could be detrimental for the part's strength. As you can see, at 10% and 25%, it's looking okay. 40% we're looking okay. 55%, we kind of start to see some hesitation in there. And you can really start to see it at 80% in here, and as well as where the bosses are filling. And at 90%, you can definitely see there's hesitation issues with the ribs. Let's see here. Let's see. Okay, and this just kind of is the flow simulation of the part. All right, and here we can see after analysis there's a difference in melt front temperature within the bosses. And because of this great, I guess, temperature difference here, there's a real issue for weld line problems here, which hurts the strength and integrity of the part. This slide shows that through Moldex's simulation, we've identified where many of the air traps are, as well as here where a lot of the weld lines are. And there we can see that the bosses definitely, there's some problems, as well as with the ribbing here. Okay. Through Moldex FEA Interface, we are now going to be able to bring the anisotropic materials and weld line strength to Abacus. Here's a boundary condition and the locations where the load is applied. And after the Abacus analysis, we see that the maximum strength is concentrated on the locations where the screws lock into the boss. The maximum value is 2.73 kgf, and the residual stress is 1.59 e to the third power. From the below curve line, we can see that there's a breakage chance when the broken force reaches 33 kgf. The changes that were made to this particular part in order to compensate for the issues that we were having was that the boss's size was increased to increase the strength and the amount of force in which they could take, as well as the designer went back through and changed his venting in order to allow for less air traps, less hesitation, and improve on the rib quality, which then in turn improved on the structural integrity of the part. Okay. Once we ran the simulation again to see how much load we can afford, from this chart, the broken rate was raised from 33 to 40 kgf, which was an improvement of about 21%. And how this really benefited was that after mass production, the product defective rate reduced by 30%. And through the iterative design using Moldex3D, the manufacturer yield was increased by 10%. Production capacity on this part was about 150,000 units per year, which once you crunched all the numbers together and the amount of parts that didn't break, the producer saved about $19,000 in total. Last couple, we'll just look at this Honda dashboard. Here we can see the flow rate. The gates is unbalanced, meaning that one gate is filling the cavity a lot faster than the others. This is an indication of unbalanced flow. We modified the gates here to improve on design, which again improved on things like weld line locations and increased better packing and less warpage. Here we have a gearbox. This company was having an issue with the short shots, and while running our simulation, we were able to locate the exact spots of the short shots, which correlated with the picture here. And here we just have a little bit of testimony from Nissan and what they thought about our software when they were using it. They said that Moldex3D is very clear and user-friendly. The icon list is, again, very clear and well-organized, which makes the software very easy to operate. And most importantly, the results were good enough to reduce their cycle time and save their costs. And in conclusion for myself, here you can see a couple of our upcoming training events. And if anybody is interested in, I guess, participating in any of these, feel free to contact us. So I will go ahead and give control back on over. About it for me.
All right. Great. Hey, thanks, Rob, for that look into Moldex3D.
Sure.
And thanks for your time. If you have any questions about Moldex, please give me a call. If you would like to, Mark Peterson at the contact information below, and we can take care of you there. Also, I should say, too, if anyone wants to show a coworker this particular webinar over again, we will have it taped on our website, so that'd be great if you could we'll show it, have it locked in so people could see it later, so that'd be great. Thanks for your time this afternoon. We appreciate that, and if you have any questions, please call me, and I will pass it on to Rob if it's something more technical. So thanks, everyone, and have a great day.
Thank you.
Hey guys, good job. Thank you. Rob, good job. Mark, can you hear me? Oh, they're hung up. I'll end it off.